all things. So the food, like the intellectual ones. To be too quick is not a good thing. Although present-day world pushes us to be quick and fast, but that is detrimental for some things. Well, a lot gets done, okay? In the past, much less was possible. And this lot that gets done, should go to benefit people. So I'm not criticizing the modern world just because I'm an old man. I think that we always go towards better things, that the past is not better than the future. So, but still, some things need time. That was true in the past, and it is true also today. I see it with my many students and so on, collaborators, okay? And so don't worry, okay, about what is happening in these classes in such a short time. Of course, if you have questions, just get back to me. And in the tutorial hours, that we have 2 tutorial hours also today, maybe there is a chance to discuss things more. Now, the amount of material I would like to cover this morning is not too much, so maybe we have time for some exercise that then you implement in the tutorial hours, okay? We'll see. We do what is possible to do. And what is not possible is not possible. Okay, so I start now. We had 6 academic minutes. I don't know, maybe other people are coming, but perhaps I should start, right? So if they come, in any case, there is the material. It is all in print, what we use, what we do today. Yeah, unless there are questions directly that I can try to answer before I start today's class. Or if questions come along, you just stop me and say, okay? Okay, so let me go back to where we stopped yesterday, which was this, the definition of the evolution of a probability measure, okay? So we said that if mu is a probability measure, maybe this probability depends on a time t. And this probability measure can be used in various ways. One is to attribute a weight to subsets of the big space, which is called phase space. Okay? And that we define it as we would do with the mass of a fluid. Now, if you keep this in mind, it will help you to see through the calculations, because some calculations get a bit involved. But you keep in mind this, if it helps you, okay, if you have physical intuition about a fluid. A fluid, for instance, a gas, the air in this room, okay? Yesterday I spoke about the water that goes from the glass into my stomach. Okay, the same thing. When the winds blow, air moves around, okay? And it carries with itself its own weight. Yes, air is thin. It's not very heavy, but it has a weight, okay? It has a mass. It has a mass. The weight comes from the force of gravity, but the mass is a property of the molecules of air. So when they move around, maybe they get compressed because there is high pressure, and then you feel hot, okay? Or maybe they expand because there is low pressure. So the volumes can change, but the mass remains the same. The volumes can change and can move from place to place. Okay? Now the winds are blowing in Delhi, hopefully. They are not blowing here. But the perturbation may move. Okay? It comes here. So the mass has moved. It has changed shape, but the mass remains the same. This is the idea. Okay? This is the idea. We think the probability is like mass. And mass at time t in a location E is the mass that at time 0 was in the pre-image. Okay? This is the meaning of this abstract formulation, but in the end, it makes sense. Why do mathematicians develop such a formula? Well, because whether they want or they don't want, they think about the real world. Sometimes you hear that mathematics is a beautiful abstract thing. Okay, it is an opinion. Okay? I think that it is that to be totally abstract is impossible, because we are made of flesh. We touch things with our hands, and these are the only things that we know. Nothing comes out of nothing. This is an old saying of the Latins. Okay? Ex nihil nihilo. Nothing from nothing. So we always have something in mind. And in fact, mathematicians give names to these things. Okay? And you will find that this is called mass in mathematical textbooks. But if it is the probability of temperature, certainly there is no mass, right? But we call it mass because that helps our intuition. So this is the meaning of the formula. Keeping that in mind, maybe that calculations look more reasonable. Okay, so this will be equal, by definition, to the integral over the set E of the probability at time t. And this will be equal to the integral over the set phi minus t e of the other probability, d mu 0. Okay? Now, we introduced the characteristic function that is 1 when you are inside E and 0 when you are outside. So you can write this in a more general form, which is integral over the whole phase space. So this can change, this does not change. Over the whole phase space of a given function, chi e, the characteristic function evaluated at the point, okay, d mu t of x, and this will be the integral over the whole m, you see it's the same, of what? Of chi, the characteristic function. Now this is based on phi minus t e of x, and this is d mu 0 of x. Okay? So these are things that you can use. Now, suppose that you are not, then when you do an integration like this, you have a function and a probability. What you obtain by definition is an expectation value, is an expected value. So we can write this also as expectation. Now you see the difference between E, a subset, and this thick E is expectation, okay, at time t, of my function chi E. This is the definition of expectation, is the integral of my function with respect to this measure. Well, you may wonder, why do I call it E? It's not me. It is probabilistic terminology. It means event. That is the probability of an event. Which event? The event of x being inside E. Okay? It is an event. What is the probability that temperature is between, today, I don't know, it feels around 10 degrees, something like that, 8 degrees. What is the probability that it is between 8 and 10? Okay, the event E, in that case, E, would be the set 8, 10. Okay? And M will be, if we want to exaggerate, the real numbers, assuming that temperatures can go from minus infinity to plus infinity. Luckily, it doesn't happen. But in some places in India, it seems that the upper bound doesn't exist. Being in the south, in some pretty hot places, even in winter. Okay, so also this helps. Now, if you integrate your function, whatever function, a function in a given function space, often we take L1. Okay? Although it is a huge space. You get the expectation value. So here you have the expectation value at time 0, because the probability is the probability of time 0, of a different function, chi phi minus t e. Okay? Now take a more generic quantity, observable as we called it, okay? We call it O. And O is just a function in our function space that goes from the phase space to the real numbers. Okay? Now we can take the expectation at time t of observable O. By definition, it will be the same thing. It will be the integral over m of O of x d mu t of x. Okay? And as we did that, we could have taken the expectation at time 0 of the same observable O. You see, there is a difference between this and this. This is an expectation at time 0, okay. This is expectation at time t, okay. So like here, at time t and at time 0, but of two different functions, chi e and chi phi minus t e. Okay? Here I'm taking the same function. So in general, these two are different. Okay? They are not the same. Now, you understand the sequence of equalities that I have written on top? They correspond to the fact that the mass is conserved. So we are saying the probability is conserved, even if it moves around. That is the meaning of this sequence of equality. But if I look at the expectation value of temperature today and of temperature tomorrow, they will be different in general. Okay? So you don't have that sequence of equality. So if you have the same function, but you change the probability, then the expectation may be different. It doesn't always happen. Okay? It doesn't always happen. It may happen. You see the eraser on the other one? By the way, Sivaraji, these markers are very nice. Yeah, right. They're good. So it could happen. It could happen that the expectation remains the same. Et of O is equal to E0 of O. If, okay, if this is true for every observable in our function space, let me call it F. If it is true for every t, say, could be real, but could be integer, like in the case of the logistic map. Okay? If it is true for every observable in the space that you have chosen, and for every time t, then okay, it is true also for the characteristic functions of the sets. Okay? Then what you have is that E0 of chi e by definition is equal to Et of chi e. Sorry, by definition. I mean by the hypothesis. Because chi e is a function. It belongs to the space. Okay? But by definition, Et chi e is equal to E0, you see, go back, is equal to E0 chi phi minus t e. So now you have this equality. Okay? If it so happens, okay, which I told you is not true in general it will not happen. But if it does, then you have that the expectation of the characteristic function chi e. But what is that? That is mu0 of e. Okay? Expectation of whatever time. Chi e is its measure, its probability. So this is equal to this. And this is equal to its to the measure of phi minus t e. Okay? But mu0 of phi minus t e is equal to mu t of e, which is here. So you know what happens? That the probability of E does not change. So if expectations don't change, probabilities don't change. And it is two-way. Of course, if the probability has not changed, the expectation will not change, because you do the same integral. Okay? If the probability here is the same probability that you have an earlier time, okay? If the probability here is the same that you have here, this integral and this integral are equal, because the function is the same. But it goes also the other way. If expectations are the same, don't change in time, then probabilities must be the same, provided this equality holds for all observables. And all observables means for all subsets of the sigma algebra that you have chosen. Okay? So things go this way. They can go both ways. There is one that is more mathematical way, and there is another one that is more physical, if you like. The physicists will like to look at the observables, because they are the things that you can measure with measurement tools, with a thermometer. Okay, so they will choose the function space. They will tell you what are the quantities that they want to measure, which means the quantities of which you want to compute the expectation. And mathematicians are open to all possibilities, but they will not dislike the idea of looking at the probability of the event rather than at the expectation values. Okay? But the two things are perfectly parallel. I choose a sigma algebra, which is a set of events of interest, or I choose a function space. You see in this sequence of equalities that can be connected to each other. Also because the characteristic functions, linear combinations of characteristic functions that are called simple functions, are dense in the space that you have. Okay, so it is very much entangled. You choose what? You choose what? Even mathematicians, however, will agree, and we see in a moment, that it is still better to work with expectations than straight with probabilities of events. Okay? Because events can be, even if you have chosen a mild sigma algebra, they can be quite ugly to look at. Okay, like fractal sets, or quite beautiful. That depends. But if you plot them on a computer, you can see beautiful pictures coming out of fractals. If you have to do calculations with fractals, it can be quite complex. And of course, some of our friends are very much experts of fractals, right? Sivaraj. Here also. So far from me saying that they are ugly, it was just a way of saying, you know, it's a complex object to deal with, not very simple. Expectations are simpler. Expectations are simpler because they are the result of an integral. And you know that when you integrate, you smooth out things. You make things easier. Okay. So this is more or less a summary of where we were yesterday. But it was good, I think, to repeat it. So when you have that mu0 of E is equal to mu t of E, we speak of invariant measure. Okay? Where did I put the mark? This means mu t equals mu0, then you can just call it mu, is invariant. Okay? Now, some miracle at times happens. It doesn't always. In fact, it is, if you like the rational within the continuous, within the irrational numbers. Okay? The rational ones are very few, although they are infinitely many, right? And the rest is much, much more. It may happen, however, that there are situations in which, too big. I know.
Second pen process. Pen. Select the pen. Just take it. No, in the same. Yes.
You want to come here, tell me?
Yes.
I don't know what to do.
No. Yeah, in the marker itself. Yesterday only we have done this. So this pen more sharper. Oh, still it is.
No.
No, this size will become very large. Yes.
Yes, okay, very good. Very good. So now, select, let me make a big selection. And then remove. Okay. Okay, pen. So, it may happen that d mu t of x equals something like this. Ft of x dx. Okay, where in your space dx, your space you have to decide what it is. Okay, if you want to be mathematically precise, you better choose a manifold, a differentiable manifold. Okay, so like a surface embedded in a larger space. But in those coordinates on that manifold, but Rn is also very smooth, is flat. Okay? This is called the Lebesgue measure. Okay? It is the volume measure. And if you have that this is the case, okay, to be a probability, you have to have that the integral over all m of d mu t has to be equal to 1, it will be integral over m of ft of x dx to be 1. Okay? The probability is always non-negative. So you also require ft of x to be bigger or equal than 0. Okay? So this is called a probability density in probabilistic terms. You see, the notion of mass comes back. It is called the probability density because the mass then is given by the density times the volume. If you integrate over the whole volume, you get the whole mass. And the whole mass for probability will be equal to 1. Okay? And for those who do statistics, that corresponds to 100%. Okay? So that we saw it yesterday. Okay? The measure of any set is a number between 0 and 1. And it is defined this way. So when you have this situation, you say that the measure mu t is absolutely continuous with respect to the Lebesgue measure. Okay? And more speedily, people can say that it is a regular measure. It is regular. Okay? Now, this situation is very rare. But it does happen in very relevant situations. So it is important to consider it. In particular, in the description of physical systems in an equilibrium state, then you are in these situations. And you have the measures that are called ensembles. Maybe you have heard about the microcanonical ensemble. It is the simplest one. It is uniform. Now I'm exaggerating, okay? Here one should be much more refined, but generically it is a uniform distribution, so it is like the Lebesgue measure. It does not have a density that changes. Density is equal to a constant, and is equal to 1 divided by the volume. Okay, so this is the microcanonical ensemble. The microcanonical ensemble describes systems that are isolated from the external world. Okay, so sometimes they are drawn like this. You have a box with thick walls. And through these thick walls, neither matter nor energy can go through. Well, then, this ensemble, this F, okay, and because it is an equilibrium state, will be an invariant F, will not depend on T, then is suitable to obtain a lot of results. There is the canonical ensemble. Please, please. Ooh, good. Good, good. There is the canonical ensemble. Okay, this describes systems that are not called isolated. They are called closed. Closed means that the walls don't allow matter to go in and out, but energy is allowed to go through. So you can give heat, you can warm it up, or cool it down. Then you use the canonical. And then there are generalizations of this that are called grand canonical. In all of them, you have something like this. In the canonical ensemble, you have that the distribution is E2 minus a certain parameter beta times a certain function h that is called the Hamiltonian divided by the normalization that depends on this parameter beta. And then the probability, if this is an h of x, where x can be a very large vector, okay, this is a volume in a very large, in a very high dimensional space, and that is what it is. Okay? If we are lucky, we get to the point of using it. So now, the problem of computing the evolution of the probability can become a little more explicit, because we can look at the evolution of the probability densities. Okay? We look at the evolution of the probability densities. So still, the definition is what we used to have. Okay? What we need is that the integral over a certain set E of now ft, it changed color. Okay. Ft of x, and now it went back. It has its own life, its own intelligence. I don't know if it is artificial or natural. Okay, so you have this, which corresponds to this integral now. Okay, integral d mu t is that integral, because d mu t is this. So this has to be equal to the integral over the pre-image of f0 of x dx. Okay? Now, if you think the pre-image, by its definition that I gave you yesterday, are all the points that in a time t will go inside E. Okay? This is all the points that have a certain mass that after a time t are found inside E, by definition. Okay? If you want, I can write the definition again over here. So, the pre-image, we'll do an exercise today. We'll do these calculations explicitly, and then you implement it in MATLAB, is the set of all points x in the phase space such that phi tx belongs to E. Okay? This is what it means. So, the points that are in here are those that after a time t are here. Well, then we can do, if we know this transformation phi minus t, we can do a change of coordinates inside the integral. Okay? We can do a change of coordinates. Let's do this. Let us substitute x with phi minus t y. And we go to the new variable y. Now you know that when in an integral you do a change of coordinates, you have to compute the Jacobian of the transformation. So we introduce the determinant, of the Jacobian transformation, which I call it j minus t because there is a minus t here, evaluated at point y, okay, by definition is the absolute value, okay, of the determinant d phi minus t by dy, okay, a function of y. Let's see if I can do it. Yes. Good boy. Okay. This may be difficult to compute, but in some cases it's not difficult to compute. When it is difficult to compute, ask a computer to do it. And sometimes also computers have their own problems. But at least they always give you an answer. Maybe the answer is wrong. So you have to be careful. Okay? Because computers are used to give, they know that they have to give you an answer. Okay? Sometimes they give you none, not a number. Then you know. Then you know. Sometimes they don't tell you. Sometimes they give you a number and you wonder, what number is this? Anyways, if you have done that, now let us write our integral here like this. Let me see. That one. Yeah, sorry, not this one. This one. It becomes the integral of f0 computed now in place of x. I have this. So phi minus ty. I change coordinates, so I have to introduce the Jacobian j minus t of y. And now I integrate with respect to dy. Now the limits of integration have changed because I changed the variables. And so you have to ask, what should I stick there? All right, now think what you should put there. Think. When I have x, I take the points that are in the pre-image of E. When I have x. When I have y, where is y to be found? Huh? Someone said. Yes, almost. This is the pre-image. So you see, this is a point in the pre-image. Okay? So, sorry, it is a point that goes into the pre-image when you take it back. Okay? I also got confused. Apologize. I do it from the beginning. X is in the pre-image. Y is a point that is not in the pre-image. It will be in the pre-image if I take it back. So it is in the image. It is in E. Okay? You reflect on it, but it's like that. Okay? This quantity should be in the pre-image. But then y should be in the set. Okay? I take a point in the set, I evolve it backward for a time t, I finish in the pre-image, so I was where E should be. Okay? But now this is very interesting. Because this is equal to this. And now they are both integrated over the same set. And now suppose that this is true for all sets of the sigma algebra that define the probability. Then the equality of the integrals is the equality of the integrands. Okay? Then you have that ft of x is equal to f0 in the pre-image. Sorry, now y is a dummy variable, right? Y is a dummy variable. It is just for integration. So whether I call it x or y makes no difference, right? It is just a label. So this is equal to f0 in the pre-image of x times j minus t in x. Okay? If this is true for all e, okay? If true for all e in the sigma algebra. If it is true for e in the sigma algebra, in this representation of the space, the sigma algebra is a representation of the space. In this representation of the space, this function is equal to this function. You have to keep this in mind, okay? Because things are a little more complex than thinking about y equals x squared. It's a parabola, it is like that over all points. Okay? When you do an integral, you lose the notion of this fine structure, continuum structure of the space, because integrating you smooth out. Okay? So depending on how finely you decompose your space, depending on that, this equality is easier to obtain or harder to obtain. Okay? And that is why then you may speak about different measures. You may speak about different forms of convergence and so on. Okay? If you want the convergence in L infinity, is harder than the convergence in L1. Why? Because in L infinity, to get equal, you have to struggle more. Okay? Equal means really equal. While in L1, equal means that the integral of the absolute value of the difference is equal to 0. It's much weaker condition, much weaker. Okay? In any case, for us, we have no other knowledge than the sigma algebra, and the functions that we use are those corresponding to the sigma algebra, so this is true. With our level of resolution, a physicist would say. I have a microscope that can look so much finely and no more finely than that. On that level, these two things are equal. And mathematically, it's perfectly correct. Okay? There is no cheating. Okay, so now we have an expression for this. Because we have an expression for this, we also have an expression for the observables. So let me compute the expected value at time t of an observable O. Okay, that is equal to, what did I write? Undo. That is equal to integral over my space M O of x. Now ft of x is f0 in the pre-image phi minus tx j minus tx dx. Okay? It's just using the definition. Let's do another change of coordinates. Now we do the opposite change. Okay? Because now here I have phi minus tx, which I don't like very much. So let me do this. Change to this time I take y equals the forward evolution phi tx. Okay? no. I have x, so I have to do the change of coordinates. Select. Erase. This is. Well, first, I eliminate also this. Delete. Then I go back to pen. So x equal phi ty. Okay, here. I want to change from x to this new variable, y, but this time it is defined in the opposite way. Okay, so this change of coordinates will have its own Jacobian, which this time I call jt, okay, because there is a t. So this becomes now equal to the integral. Now watch out, because we are going to obtain in a minute a very important result. Integral over m. You see, here I don't have to worry about the set, because I'm integrating over the whole world that is available. So whether I use one set of coordinates or a different set of coordinates, the whole world remains the whole world. Okay? If I have to integrate over the whole real line from minus infinity to infinity, and I change variables, I still integrate from minus infinity to infinity. Okay? So this is the meaning of this. Now, O contained x, so now it is evaluated in the point phi ty. F0, F0 is evaluated at phi minus tx, where x is phi ty. So I do t step backwards, and then t step forward. So this is just y. Okay, now you remember that yesterday we said we want this group property. It is still there, huh? Did I do something wrong? No, yeah, I can do something wrong. Huh? Don't you tell me. But what was the comment? Phi t compared with phi s, composed with phi s is phi t plus s. You were repeating this, right? Okay. Now s is minus t, and then I have t. T plus minus t is 0. Phi 0 is the identity. Okay? So, whichever way you look at it, you have y. But also think of this. I walk forward in time for a time t, and then I walk backward for the exact same time t. I end up where I started, in the identity. Okay? So, now we have the Jacobian, j minus t computed. Now, this is the thing that you have to keep in mind, and thinking of fluids will help. So x is phi ty. And then, so this is the old function. Now, because I changed coordinates, I have to introduce the Jacobian, which will be, this time, jty dy. Okay? Any question, observation? You want to say something?
As we already defined j minus t of y, the absolute value del of the phi minus t upon del y upon y. So we can put it here.
Yeah, didn't I do it? So, come, show me. I'm not sure I understood what. Let me see in my notes if I did something wrong. No, don't be afraid. Okay, I do wrong things all the time. Come. Because you know, this is also something that I use as an excuse with my students. Because from there, you see things that from here I cannot see.
At that, what I was thinking,
Yes.
you already defined it here. So I was just putting it here, like this value. Calculating, and whatever we will get, we can put it.
Oh, now I see you want to do more than I wanted. because the y is not the same y. There are two different changes of coordinates. So I'm not sure that you can do that operation. I'm not sure, but I have to think. Maybe you are right. But this y here came from this. And this y here comes from this. So there are two different transformations. Okay? But maybe in the end it's the same. I'm not sure, because what I'm going to get is something trivial. Okay? So then you tell me if it was what you had in mind. Okay? But for the moment, I just go back to what I had. Takes well, anyway, I know what to do. I select this. Then I delete it. And then that frame doesn't touch anything, okay? Now I ask you to think, now for a given single y, which could be what you have in mind. I'm not sure. But here I know what I have. I have a single y here and here, like throughout. Okay? The y is the y. Think what happens if you start. So I am here, a starting point. Okay? My point is y. Here is y, okay? You remember. Here is y. Now I move for a time t, okay? And the mass that I had here, after a time t and doing some wobbling, okay, arrives here. This is after a time t. This is phi t y. So the Jacobian of this transformation, you know what it represents? It represents the factor by which the volume has changed. So suppose it has expanded, it has become like this. Okay? That is what the Jacobian represents. Okay? In hydrodynamics, this is clear. But we use probability as if it is a fluid. We are in a much more abstract and sophisticated space than the three-dimensional space where the glass of water lies. Okay? But the idea is the same. So I was like this back, and I'm like this here. Okay? The factor of change, which is a growth of the volume, is this one. Right? Suppose the volume doubled. Then this is 2. Okay? Now think about this. What do? You start from phi t y. So now you start from here. Now you have a volume. And now you go back by a time t. It is the same points. It's the same dynamics. So if going forward I double the volume, going backward, what do I do? What is the product of these two? 1. Now this can be computed mathematically. But just knowing about fluids, you know that that factor is 1. Okay? We will... Yes? Because they are so good. So, the rule that I described in words... Yeah. The rule is this. Is J minus t of phi t y, okay, is equal to 1 divided by jty. Okay? Yeah, I wrote it correctly. So this is 1, and that allows us to write, I will pull it up because you have already seen, oh, it doesn't want to go? Yeah. This allows us to write the result that I told you is very important. The result is this, is that the expectation value at time t of O is equal to, now you see, this is 1. So here you have the integral of O with respect to the measure J0, mu 0. So this is an expectation at time 0. Ooh, no. I hope. Oh, I'm sorry. Let's now we find out. Expectation of what? The question is expectation at time 0. Yes, because we integrate through f0 dy. So it is expectation at time 0, but of which function? Not of O, but of the function O composed with its time evolution for a time t. Okay? Let me put it more explicitly. What do I mean by O composed with phi t applied to x? Well, I mean, what is there? It is O of phi t x. It is a different function. It is a different function. You know that even with a parabola y equals x squared, if you change coordinates by shifting the origin of the axis, the form is different. Same thing. Same thing. Only in a more abstract, more general sense. Okay? So, why is this result important? What is written here? And then maybe we have our break. Oh, still 4 minutes more to go. We have that the expectation at time t can be obtained as the expectation at time 0 of the evolved observable. So the evolution of the expectation, the evolution of the probability can be cast into the evolution of the observables. I try to tell you all the way along that there is a strong connection between the two things. You define probabilities with observables and observables with probabilities, expectations of observables with probabilities, so these two things have to be related. Now, why is this important? Well, to give you an idea, you have this in quantum mechanics, and it is called, they gave it a name. It is called the equivalence of the Schrödinger to the Heisenberg representations of quantum mechanics. But it's just this, it is a change of coordinates. But why does it get a special name? Because it allows you to compute something that could be very difficult. Because go back to the definition of mu t. It's not easy at all. Yeah, it is easy to write this sequence of equalities. The equalities are true, but now tell me what it is. Very difficult. In particular, suppose that this is clustering on a fractal set. Okay? It becomes a very, very complicated distribution. What happens to f? What happens to f going from f0 to ft? God knows. But the initial state is your initial condition, so you know what is the initial state. So if you can preserve integration with respect to the initial probability, then you are much happier. Of course, nothing comes for free. So you will have to evolve O. But one thing is to evolve O, which means solving the differential equation. And one thing is to evolve the probability, which is much more complex. Okay? So this is a very useful equality, extremely useful, and conceptually important. It says that you can evolve probabilities or equivalently evolve observables, and the result will be the same. Right? This is quite a lot. Now, to conclude this hour of lecture, I want to give you one formula that you can get out of this one. Now, let me see where I put it. We have seen this. Yeah. No, I already gave it to you. So we can have our break now. Okay? Thank you for being patient. Also for your contributions to what I'm doing at the board. And when now we have a break, what time do we come back?
After 20 minutes. Yes, boss. After 15 minutes.
15 minutes.
So after coming, you please sign the afternoon sheet for yesterday.
I had a conversation with our colleague that, sorry, I don't know your name, even if you told me. Maybe you didn't tell me, right? Did you or didn't? Okay, so, but it would have been the same. Because, unfortunately, I find it very hard, and please don't take it personal. If you told me your name, I don't remember, because I hardly remember mine. Like I never know what is left and what is right, okay, and these sorts of things. So you have to bear with me. And you know, she made a remark that I said I have to think, and the reality is that I have to think. Okay, because then I said, look, it looks a little different from what I'm doing, but in the end the result seems to be the same. So if the result is the same, there may be a reason. And I don't know if during this week we'll have time to think about that, because time goes fast. No, but you see, I teach this stuff, so I should know every single detail. Okay? And if there is a new one that I haven't thought about, maybe it is revealing of something. So I'm happy of any comment you want to make. And even if the comment is not exactly to the point, it does not matter, because it's still something that allows you to think more and get to deeper results. You know, I spent a number of years in the United States, and what they taught me there was, there is no stupid question, okay? Every question is an interesting question. So when you are in class and someone asks a question, your first thing is, maybe in Australia it's more the same, I don't know, you tell me. The first thing you should say, this is a very interesting question. It is not hypocritical, it is true. It is true. And often, things in fact open a new way of looking at things. So, for those of you who are interested and who just joined, what I've been doing yesterday and today so far is in a PDF file in the folders that Professor Sivaraji can share with those who want. You already sent?
Yes.
Also to them?
She actually did not contact me.
Yeah.
All others.
Yeah, okay. So that is Professor Sivaraji. Yeah. That you can guess he comes from a hot place. But I don't tell you why. You don't know, he's such a good man. I'm so fortunate to have met Professor Sivaraji. Okay, so after these many words, more or less everybody's back. So we start. Let me see the time. Okay. So now we are going to speak of the Liouville equation, in fact, what is often called the generalized Liouville equation, which is the thing through which, in a more practical way, you compute what I have written here. Okay? So here we had an initial probability distribution F naught in our space M, okay? And we have found a recipe to compute what it becomes after a time t if you assume the probability moves like a fluid in real space. If probability in phase space moves like a real fluid in three-dimensional space. Of course, the two things are not the same, right? I will never stop telling you that if I throw you a stone, which I would never dream to do, that may hurt you. If I throw you a lump of probability, you don't feel anything bad. Okay? Probability is not matter. But nevertheless, we think of it as if it is something material. Then big questions come about what do you do with it? Because with the stone, you know what you could do. Not only hurt people, but you could use it to build a wall, okay? You can do useful things. And probability, is it useful? Okay? And the answer is it depends. It depends. But we are going to talk about the cases in which it is useful in the coming lectures. And so, even if we do it abstractly, keep in mind that it will be used. So we start from this thing. We start from having a phase space, M. Why I denote it M all the time? Because it stands for manifold mathematically, okay? It is a more precisely defined object in which it is possible to put coordinates and then do all the calculations that I've done. On any generic set, that is not possible. Okay? That is not possible. It's not possible to compute the derivatives of the dynamics if you move in a space with corners, for instance. At the corner, the derivative, you don't have it. But the derivative position is the velocity. The velocity is important. Okay? So you want to be in a decent space. R3 is very decent. But we may think that our space concerns a set of how many? N particles. And that these N particles move in D dimensions. Okay, so for instance, I move in three-dimensional space. D would be 3 in my case. And if my particle is a little sphere, then maybe under certain circumstances, it is enough to look at the center of the sphere. The center of the sphere has got 3 coordinates. Okay? So like me. But if the object is more complex, say it is like a molecule made of 2 atoms, then one position is not enough anymore. Maybe you give the position of the center of mass, and then you give the angles with respect to which this goes. So here you have 5 degrees of freedom. Okay? Because it is 3 degrees of freedom for one sphere, 3 degrees of freedom from the other sphere, and then you put a bond between the two that reduces to 1 degree of freedom. So that in that case D is 5, even if they move in three-dimensional space. Okay? So this to give you an idea. Now, of these particles, you are interested about the positions that are commonly denoted by Q. And I use capital Q because positions will be a big vector. A big vector that has dn dimensions. Okay? I call Q this big vector. And the other quantity that we like to consider is P, momentum, that when you have a fixed mass, okay, corresponds to the velocities. Now, for every degree of freedom, d, there are, for position, there are as many velocity directions. So, the overall point in M, okay, will be 2 dn dimensional. Okay? Now, if, as we have been discussing so far, probability is like the mass of a fluid that moves in a certain space. For mathematicians, that the space is 3-dimensional or 6-dimensional, or say if this is the number of atoms in a cubic centimeter, like air, you would have n equal to 10 to the 19. So this space is not high-dimensional. This space is huge. Okay? This space is huge. That number corresponds to a rarefied gas, like air more or less is. It's not very thick. On a solid, you would have 10 to the 23, more typically. You know where this 10 to the 23 comes? Geographically, it comes from Torino. Avogadro, okay, Avogadro's number was one of the many scientists who grew up and did their work in Torino, okay, like Lagrange, like many others, Peano. But this is, as we say, thin air. So it is 10 to the 19. It's a small number. No, it's not small. We have no perception of what is 10 to 19. You think you know just because I wrote it? No, you don't. Try to think, look up in the web, what is the shape of a sphere in high dimensions. Okay? As you go to high dimensions, it becomes something very rigged. You will see why. Still, the equation of the sphere is not smooth at all when n becomes large. So anyway, this is to tell you that mass is very different from probability. Very different, because even the space where it lives is very different. Okay? However, if we make that assumption, then we can consider the variation of mass, the variation of probability as what is you obtain by looking at what goes in a certain volume, that is 2dn dimensional, and what goes out. The difference between what goes in and what goes out is the variation. Okay? So if this is a volume of infinitesimal size, call it dx, and you look at its variation in a time dt, then it is just a simple calculation. You say what you know, you have, when you go out at time t plus dt, and you have moved by an x plus dx, you can do the difference with respect to what was before, okay? And then you divide by dt and you obtain the derivative. Now, I'm not going to do this construction. It is the same that you have in hydrodynamics. It's called the continuity equation. Now, the equation I'm going to write, that is called Liouville, generalized Liouville equation, is the continuity equation not for a fluid, but for probability. But it looks formally exactly the same. So, what would you get? Suppose that our points, gamma, move in time according to a certain law, g of gamma. Then, okay, is this simple calculation leads to this equation, that the derivative of probability with respect to time is equal to minus the divergence that comes from considering the dx, okay, minus the divergence of the quantity that you want to transport, which is the probability times the velocity with which it is transported, which is gamma dot. This is called the continuity equation for a fluid. Okay? Now we can make it more explicit. This is equal to minus the divergence. Divergence, let me make clear, it is in this space where the variables are gamma. It's not in the real space, okay? Divergence of gamma of f times g. Okay? And because you have the divergence of a product, just by the rules of derivatives of products, you get that this is equal to minus g, remember there is this minus g scalar product of the gradient of f. So f is a probability density. You remember it is a scalar function. Okay? F goes from m to the interval 0 infinity. It's not negative, okay? And its integral is equal to 1. So f is a scalar, you can do the gradient, you obtain a vector of the same dimension as the vector field G. Okay? G is called the vector field. It's a vector because it has the same dimensions of the derivative of gamma, which has the same dimensions of gamma, okay? Which is 2dn dimensional. So you have minus g scalar product with gradient of f minus f divergence gamma of g. Okay? Now I'll give you an intuition, even if I didn't do this calculation, of why this makes sense. Again, thinking that it is like a fluid. But this is called the generalized Liouville equation. Now, you know, some of my friends did some historical research, in fact, friends from Australia, to find out that Liouville never wrote this equation. It is credited to Liouville. Like Navier-Stokes equation is not to be credited to Navier or Stokes. Never mind, life is like that. But we all have to decide to use it anyways. So generalized Liouville equation. Let's see how I can write it again. If I introduce a quantity, lambda, where is it? Well, lambda, which is the divergence, gamma, of the vector field, what does it represent? Well, it represents the rate at which volumes contract or expand. Okay? The same for a fluid. It is related to these Jacobians, but these Jacobians were computed over an extended period of time, t, while that is just the rate at which things change, at which volumes change. So lambda bigger than 0 means the volumes are expanding. Lambda smaller than 0 means the volumes are contracting, and lambda equals 0 means that they stay what they are, even if they can get deformed. Okay? So if you write it that way, the equation can be put in this form. Passing to what is called the total derivative, df by dt, okay, which by definition is the partial derivative of f with respect to time plus the contribution of streaming, as it is called, G scalar gradient gamma of f, okay? This is just the definition of total derivative, okay? It is called, in fact, Lagrangian, from Lagrange from Torino. If you come to Torino, I show the statue, and there are some funny stories, okay? Lagrangian derivative because it represents the variation with the motion of the fluid. Okay, so here the partial derivative means I'm sitting at a given point and I look what happens as time goes. Here I follow with the motion and I look what happens around me as I move. This is embedded in here. Okay, now, but you see, you just substitute, okay, and what you obtain is this pretty nice thing, is minus f times lambda. Okay, so now let's think why this makes sense if we treat probability as a fluid. It does make sense because if I follow the fluid in its motion, and while it moves, it expands or contracts, what happens is that the density will change. If it contracts, the density becomes higher because there is the same mass in a smaller volume. And if it expands, the density goes down. Now, this derivative says that if lambda is positive, volumes expand, then you get a negative variation. You go down. And if lambda is negative, volumes contract, then the density increases. Okay? So it is consistent with our previous picture of probability like a fluid. And then, here we have to go back to some notion of measure theory, but don't worry too much about that. Suppose that f is strictly bigger than 0, not as I wrote there, okay? In places, if it gets 0 in some places, you have to develop some particular technique. But very often, if you have a probability density like an exponential here, and you have a smooth vector field on a smooth manifold, this will remain bounded away from 0 all the time. So it starts different from 0 and it never reaches 0. So these are good, the situations that are good to treat. The other ones can be treated, but they're not so interesting here. So take f bigger than 0, then you can divide by 0, by f, and you get 1 over f. Derivative of f with respect to time is the total derivative of the logarithm of f. Okay? And the total derivative of the logarithm of f will be equal simply to minus lambda. Lambda is the divergence, okay? So it is a scalar number. Okay? It is a scalar number. There are dynamics for which the Liouville equation had been developed first that are called Hamiltonian. And they have a special property. Oh, again, you always stop me if you have some doubt or curiosity or whatever, right? Oh, sure.
Just a curiosity that you explained very well here what is the point of negative sign before x. Is this the same reason when you have written generalized Liouville equation there is a negative divergence?
Yes.
What this negative sign representing here?
Yeah. So you mean in this other form here, right?
I got the answer
Yeah.
here down there, but not about that.
No. It is a good point. It clarifies also the derivation. Okay. So these take two different names. Okay. This is called the representation of Euler. So this is Euler version of the Liouville equation, and this is Lagrange version. Okay? In the Euler thing, you sit at a point. Okay? You sit at a point, and you see the probability flow through. Okay? Now I draw it in this direction, but it could be in another direction. So, in a time t, how much probability has passed through? Okay, it is the velocity times the mass that you had. The mass should be multiplied, the density, by a volume. Okay, because you see, suppose that this is time t. Then, on this side, there is a certain amount of mass, okay, in my volume dx, which in the time t will be on the other side. Okay? This at time t, this at time t plus t. So, the same mass that was here, which was f dx, okay, now has gone on the other side in the time t. If you divide by the t, okay, so you have traveled a distance dx in a time t. And so you get the velocity times f. Okay? If I still haven't if I have a larger set, that is the thing, okay? But you have that the x appears both as what goes through and as, of course, divided by the t, the velocity. So the Lagrange, which is the Euler version of the continuity equation, that is what it does. It tells you that the variation of f, okay, is equal to minus, because by passing on the other side, you lose something where you were, okay, minus the velocity times what was transported. Now, in this case, what is transported is the density of probability, but it is the same for any other quantity. Okay? For any other quantity, you have that you pass in a time t a certain amount of whatever that is proportional to the velocity, or you lose. So this is proportional to the velocity and to the quantity that you are transporting. So this is called a flow. Okay? This is a flow of f. And what you lose or gain depends on the direction of the velocity. Okay? Now, you can rewrite that rather than sitting at this surface, you can rewrite it following the motion. And then, if you go with the motion, the only thing that happens, you don't lose or gain anything. You only compress or expand, because you are going with the mass, so you are not losing anything. Okay? So this is the difference between the two pictures. Okay? Then, what is the velocity for us? In our space, position is gamma, velocity is gamma dot. But then, gamma dot is the differential equation that we want to solve, and that is the vector field, so that's how it becomes this. Okay? But, yeah, I'm glad you asked, because maybe also this clarifies a little more what we are doing. Now, for certain dynamics that are called Hamiltonians, there is a function, okay, it is called an energy function that depends both on the coordinates and on the momenta. It is the same function that you have here in the canonical ensemble, as I said. And if particles have one such Hamiltonian, then you have that the derivative with respect to time, total derivative of Q is expressed as P over M the mass of particles if they are all equal. Otherwise, this is a vector. Each component of this vector should be divided by the proper mass. And dp by dt is equal to minus, sorry, let me write it differently, is equal to dh by dp, and this is equal to minus dh by dq. These are vectors, okay? H is a real quantity, is a number, okay? But these are gradients with respect to the coordinates of P and to the components of P and the components of Q. So this is called Hamiltonian dynamics. If you go and do your calculations under certain assumptions which amount to the validity of Schwarz equalities of the equality of symmetric double derivatives, okay, you get that lambda is equal to 0. And this is called the Liouville theorem. Okay, this is an aside, okay, just to let you know, but because what I'm going to tell you has been developed within this framework of Hamiltonian dynamics. Okay? Because lambda will become the divergence of this, okay? Now, very loosely, I'm not doing rigorously, okay? But if you do the divergence of this vector field, you get the derivative squared of h done with respect to Q and with respect to P for the first part. And then you have plus, which brings in a minus, the square derivative of h with respect to P and Q in opposite order. So if you are in a simply connected set, and these derivatives are continuous, then they are equal. Their derivatives are continuous. Then they are equal. And so you get this minus this, which is the same, and you get 0. Okay? I didn't give it rigorously, okay? It's just very quick. But as a curiosity. So the dynamics that are better known by physicists have this property. The volumes in phase space neither contract nor expand. They can move. So probability can change, but without changing, because density moves from place to place, but not because it is compressed or expanded. Okay? But the other situations are much more general. Okay. In this case, of course, the Liouville equation then becomes df by dt equals 0. Okay? And that is what is called the Liouville theorem from other points of view. Okay, so now the question is, can we actually compute this thing, going from f0 to ft, using the Liouville equation? Okay, first we do a formal derivation, then we do a more concrete one, okay, of the solution. And then you find more details in my notes because calculations can get long. Maybe I come here. Can I erase the board in just one? Clear. Ah, beautiful. Okay. Where is it? Yeah. So we do this. We introduce an operator, L, that stands for Liouvillean. That is defined like this. Minus I, divergence gamma of G, plus G scalar gradient with respect to gamma. Okay, which you see, apart from I, is what we have here. G scalar gradient, and divergence. Now I. Why I? Because I want to evolve a probability. Okay, so if I introduce this operator, I have that my generalized Liouville equation takes the form df by dt equals minus I LF. Okay? I just substituted. Why is this useful? Because that I allows me to produce a unitary evolution. And probability is always normalized to 1. The integral of the probability density has to be equal to 1. So in the L1 norm, that does not change. And so I want a unitary evolution. And this I reminds me that I'm doing it. It was not compulsory, okay? Also this will preserve probability. Why does it preserve probability? Well, precisely because we have computed that the variation is due to the flow, but nothing is gained and nothing is lost. So in the end, this preserves probabilities, but written like that is more suggestive. And also for people who are familiar with quantum mechanics, that is similar formulas, but it's very different. Quantum mechanics is in L2, where, for instance, you have a scalar product and many other things, and probabilities as the square of functions, while we are in L1. Anyway, if you write the equation that way, a formal solution, you will have to give a lot of conditions to get it right, but a formal solution is this. F at time t of gamma is equal to the operator E2 minus I LT applied to F0 at time gamma. Honestly, so far we have not gained much. Even if this way of writing things was correct, not just formal, but was concrete, it's not so evident, okay, what it means. It is an exponential operator which contains quite complicated differential objects. So it is a differential operator, quite complex. But look, if you say that this equation makes any sense at all, it means that the limit of the incremental ratio exists, because the derivative exists. So now you know conditions under which derivatives exist. And let's get them for granted, simply because I dared to write this. So I have already assumed that derivatives exist, and so that if I write f at time t plus delta t in point gamma minus f at time t in the same point gamma, okay? So I am in this description where I don't change the point, divided by delta t. When delta t goes to 0, this gives me the solution. Sorry, this gives me the derivative. Okay? So, this is equal to minus I, operator L applied to f at time t, computed in point gamma, plus a correction, which is order big O of delta t. Okay? So that now, if I want advance from time t to time t plus delta t, I have to multiply by delta t, so this becomes higher order in delta t. And when delta t goes to 0, that goes to 0. And if this limit exists, if delta t to 0 exists, then I'm solving the solution with an approximation that is this one. Starts from time t equals 0. Then we will have f at time delta t of gamma equal to I have multiplied by delta t, and I take f0 on the other side. So this will be equal to 1 minus I L delta t f0 of gamma plus order delta t squared, which is what you would do on a computer using the simplest of schemes, which in fact is called Euler scheme of integration. Okay? Now, you do the calculation, okay? If you want to go to 2 delta t, then check, homework, 1 minus I L delta t to the second power. This is an operator, it means it has been applied twice. f0 of gamma plus 2 errors of order delta t squared. Okay? The errors may accumulate and become large. But if all the mechanism works, you make delta t smaller, and so you get a better solution. That's why on a computer, when the integration scheme doesn't seem to give the right stuff, you try to reduce the time step, for instance. Okay? So, after a while, you get to Fn delta t of gamma. And this is equal to 1 minus I minus I L delta t 1 minus L delta t to the n applied to f0 still in the same point gamma plus n errors of order delta t squared. Okay, here I'm playing conservatively. I'm saying that the errors continue to add up. Sometimes they may cancel each other, okay? But so this is a good thing. And now I want my n delta t to be equal to the time t at which I want the solution. Okay? So t is fixed. And if I reduce delta t to get closer to the reality of the derivative, then I have to increase the number n. I can do it. I can do it. What do you get? Well, in the first place, you get that the errors go away. Because order n delta t squared, okay, you have that n will be equal to t, which is fixed, divided by delta t. So this is equal to order delta t. Okay? And if you let delta t go to 0, this goes to 0, right? n is t over delta t. So plug here t over delta t, t is fixed. Okay? So it is order delta t. When you take delta t to 0, the error goes away. And then you have this. Then you can write ft of gamma as the limit for n that goes to infinity of brackets 1 minus I L t over n. This is our old delta t. That applies to f0 of gamma. But this is one of the definitions of the exponential operator. You want to compute the exponential operator? Sorry, there is an n here. What you do, you construct this operator, which now is not strange, okay, because there are only iterations of the known operator L. Okay, so this is practical. Concrete, sorry, is not very practical, but is already concrete compared to what we had up here and what we had earlier. Okay? This is already concrete, but not very practical. But this defines the exponential operator e2 minus I LT applied to f0 of gamma. What is this operator? Is this limit. How can you reconstruct it accurately? If you want more accurately, you only have to work a little more. You have to go to a higher n. But at every finite n, it is computable. First way. Okay? Second way. Now, you know, there was a very famous mathematician, Mark Katz, Polish, who used to work at Rockefeller University in New York. Who used to say, be wise, discretize. Because you see, all these continuous expressions are always a bit suspicious. Because the hypothesis of continuum is beautiful and very handy, but it also hides a lot of things. When you are in a discrete environment, maybe calculations are not that easy, because it is much easier to do a limit, as we said yesterday, for n going to infinity, than to say n equal 1000. Okay? Maybe not easy, but you know what you are doing. In the continuum, sometimes you don't know what you are doing. But the two are connected, as you see. The two are connected, okay? This is perfectly defined, and this is that limit, which means I can get as close as I like. To the limit if I have enough resources. Okay, now let us solve it through the Lagrange version. This already becomes a little more practical than this. Because then, is it written in proper way? Yeah, this. Okay. Then you have to remember what the Lagrange, what the total time derivative means, which means this. For Euler, what I did, I stayed in point gamma and advanced only the time. Now, as I advance the time, I have also to move the point. But I have the rule how it has to be moved. Okay? I know how it has to be moved. So, you will get this thing. D log of f. D log of f, by the equation, is equal to minus lambda, say, let me call it ds, the increment in time. Okay? That means that I can do an integral from the initial point to the final point of this thing, and then I will have to do the same integral on this other side. Now I have to ask, what are the initial and the final points for both of them? Well, for lambda, that is the easily defined function that we have, it is easy to see. It is integral from 0 to time t of what? I made it too wide here and too narrow there. Lambda, I have to follow it along the trajectory. So it will be phi s is the operator that advances the position integrated by ds. Okay? So I integrate lambda along the trajectory. We did it yesterday to compute averages. And here, what do I have here? What are the limits for f? The limits for f are that f starts as f0, computed at the point gamma, and at the end of time t, it becomes ft computed at the advanced point phi t gamma. Okay? At time 0, you have f0 at point gamma. At time t, you have the new probability, ft, where the point gamma has arrived. It has arrived at phi t gamma. Okay? This phi t solves the differential equation gamma dot equals g of gamma. But this is an exact differential. So this is log of ft of phi t gamma minus log of f0 of gamma, which is equal to that. Okay? Well, now you can invert the log by taking the exponential. If you take the exponential, you get ft divided by f0. Now we assume that f0 is always different from 0, always larger than 0, so this division causes no problems. So from here, then multiplying by f0, or if you want, let's do it, ft of phi t gamma divided by f0 of gamma will be equal to e2 minus integral from 0 to t of lambda along the trajectory starting at gamma. Okay? Now multiply by f naught. And you get this. Okay? Now this is much more practical because lambda is a scalar function of which you have an explicit expression. The dynamics you have to assume that you can solve because otherwise you do nothing. But if you cannot solve analytically, you can at least integrate numerically. And unless you end up in very strange situations, the numerical solution can be made as accurate as you like. So this exponential can be computed. This is the known initial distribution. So something known times something that you compute gives the new f. We can rewrite it a little differently by changing the coordinate, but here we are not inside an integral, so we don't need to do the Jacobian. Okay, we could introduce x equals the final point phi t gamma, which means that gamma is equal to phi minus t x, which we have always been in the situations in which the inverse of an operator, of this operator, exists. So this becomes ft at point x equal to e to minus integral from 0 to t of the function lambda computed at phi s applied to gamma, which is phi minus t x, so it is phi s minus t for the group property, okay, applied to x, integrated by ds. And now f0 is evaluated, think where? In the preimage that we have been dealing with all time. Phi minus t x. So this gives you the solution of the Liouville equation. Now, if you want, you can introduce a new variable u equal to s minus t, and this becomes then an integral from minus t to 0. Okay, but this is already the solution. You can look up on my notes more details about this. But now, homework. You remember what was this? This was the Jacobian. This was the Jacobian. Now we have an explicit expression for the Jacobian that I had written only formally earlier on. Okay? This is J minus T of gamma. So now you know what is the Jacobian. Now you can check, this is the homework, that the product of this Jacobian times the other one is in fact equal to 1. And here now the story is a bit long, so you have to... It was a useful result that we got by the intuition of the fact that if you multiply one Jacobian expressing an expansion of a volume going forward in time, and the Jacobian expressing the compression of the same volume going backward in time, the product of these two has to be 1 because you went forward and came back and nothing changed. That was based on the intuition, correct, because we said probability is a fluid. Then things are two. Either you shouldn't say that, or if you say, the product of those two Jacobians is 1. But this is a mathematical proof. Of course, I went quickly through the calculations because we know okay, that the mathematics could be fairly more complicated if you want to do things rigorously. But what I'm doing is fairly rigorous. It is correct under the usual assumptions of smoothness of the vector fields, of the manifolds, and so on. Compactness of the manifold has to be compact also. If it is not compact, a lot of these things still go through, but you may have to be more careful. But we have another expression that it is even better than this one. Okay? Is even better. That comes from introducing a function that is called the dissipation function. Okay? And this is something that I have developed with my Australian colleagues. The dissipation function is defined this way. Omega is a scalar quantity that depends on our distribution F, probability distribution F. And I define this function like this. Minus lambda of gamma plus G of gamma scalar with the gradient gamma of logarithm of f. Okay, now this function may look strange, but I tell you, okay, in the field of molecular dynamics, where it has been developed, it makes a lot of sense. It represents the dissipation of energy. And so for those of you who are familiar with the terminology, what is called the entropy production, okay, of systems that are close to equilibrium but not in equilibrium. Okay? And that depends on the choice of f. You change f for the same dynamics, which means g does not change and lambda does not change. If you change f, you get a different omega. That's why I call it omega f. Also, in applications, you may know what omega f has to be. Then you have a differential equation to be solved and know what f should be. Well, it goes either way. Normally, you know what f is, and you get omega. But you can turn it around the other way. Omega could be known, and then you get f. If you write it that way, our Liouville equation in Euler form becomes df by dt, computed at the point gamma, equal to f of gamma omega f of gamma. Now, you see, here you don't have differential operators anymore. okay, because they have already been applied to the logarithm of f. So now you have only functions. Okay, there are no more complicated operators like that, and then you have to do the exponential or whatever. Okay, so this is a function times another function, and that a little more directly, still doing the integration step by step, but only in advancing in time, like here, you get that ft of gamma is equal to the exponential of integral from minus t to 0 of this dissipation function omega defined with the initial distribution f0 along the trajectory that multiplies, so it is not acted on anymore, okay? These are numbers. This number multiplies this number at the same gamma. When you see the difference with this other solution, you want to know the solution at x, you have to integrate backward in time. That is not very handy. Again, that thing has a lot of consequences. That will be the last part of our course. Let me see, where are we? Where did I put? Ah, here. And if you are patient enough, you have to do some calculations, but they are possible. And again, you find them in the relevant literature. Now we have a new possibility to express the expectation value of an observable O at time t, okay, which by definition, I remind you, it is the integral over the whole space of O integrated with respect to the probability at time t, which is ft of x dx. Okay, this thing, which we found that was equal to E naught of the observable advanced up to time t, okay, so expectation times 0 of this observable at t fixed. So this is a function of space. O goes from M to R, okay? Now this can be expressed in this form that you find implemented in one of the MATLAB codes that I have written for you for the tutorial. And the form is this one, but today you don't use this directly, okay? Today first we work with the pre-images. So this is equal to the expectation at time 0 of the observable O itself plus an integral from time 0 to time t of the expectation at time 0 still, okay, of the observable O composed with phi t times omega f0 integrate, sorry, phi s integrated ds. Okay, this is called a correlation function, time correlation function of the observable O with the dissipation function omega. Okay, called correlation function. And correlation functions are very useful statistical tools from which we get, in particular, the response of a system to a perturbation. Now, here I have already gone to the end of the course, which is this formula. Note that this is an exact formula. Okay? I just tell you what I mean by response. And then I think that for today we are done, right? So, sorry, for the classes. Then there is the tutorial in the afternoon, right? We said that the quantities really of interest are not the dynamics in the phase space. Because in the first place, the phase space is a nightmare. It's really a nightmare. But beautiful, if you like to work with that kind of things. But from the point of view of applications, it is totally unpractical. What you like to know are the expectation values of quantities, of relevant quantities. They may make a suitable function space, like L1, or like the analytic functions, or even less. For physicists, say 5 to 10 functions O are more than enough, more than they need. Okay, so we're interested in expected values. These expected values may change in time because something happens in the world. Okay, like the expected temperature today is not expected at this time of the day. Is not the same that is expected for tomorrow, I guess. Okay. In any case, it's not this evening. The expected temperature is not the one that we expect now. Okay. So expectation values may change in time. How do you compute them? This is one way. Okay. If you know the dissipation function, if you know the equations of motion, the hidden equations of motion that you don't want to deal with too much, you can come up with expressions that tame the difficulties quite a bit. And this is one of them. Okay? Now, what is response theory? Well, response in this case would be this. At an initial time, I had a certain situation that was stationary there peacefully. Okay? Then something has happened. At time 0, something is switched on. For instance, when we came here, I don't remember, maybe the lights were off. That was an equilibrium state. E0. Expected value of the light coming from there was 0. No light coming from the neons. Now someone switches on the light. There is a current flowing through, and now the expected value of the amount of light coming has changed, has become ET, and when t is sufficiently large, it may reach a constant value, which is what we see now. Okay? This is what we see now. We see that the light is constant. It has tiny fluctuations. Okay? It has tiny fluctuations. If the neons are not very good quality, that will disturb your eyes. But fluctuations are there. The important thing is that they are below a threshold that disturbs you. When I was young, there were these stroboscopic lights in disco places, okay, that do, okay? And you'd see people doing like that while they were doing this. But because the light goes off, and when it comes up, it has moved, okay? So it was considered the top of technology in those days. So generally there will be a transient within which things go from a certain situation to another situation that were both stationary under the different constraints that you have applied. So the new situation, say, for instance, for time large, usually it takes time that is large compared to the molecular times. Okay? Remember that a molecular time is something that goes from 10 to minus 10 to 10 to minus 14 seconds. Okay? So 1 second is a large time because it is 10 to the 14, 10 to the 12 elementary times. Okay? So you go from one situation to another through a transient. This formula describes what happens to the transient in response to whatever someone has done at time 0. You can do something else, which we do in the tutorial. You can have a stationary, so how can you change things? Well, you change the forces that drive you away from your initial peaceful state. Okay, so we can relate through this formula the response to an action by sticking the form of the action inside this integral. And we'll see how we can do it. Okay? And then maybe you can change the driving force, and that will produce a different response. Okay? These things are very, very important in technology and in a lot of applications, as I told you these days. I even apply to muscular dystrophy and to neuroscience and to whatever other things you like. Well, not me personally, but people do. People do. Okay? Then later in the afternoon I tell you in practice how we use this formula. But in the MATLAB, small MATLAB codes I have prepared, some of these things are already computed, are already implemented. Now you have to work with the parameters, change things, okay? Any questions?
Does this field depend upon any kind of dimensions?
Sorry, what about dimensions? What is the question?
You started your presentation writing number of particles, and
Yes.
P is a dimensions, and then you make a system.
Yes.
So does this depend upon any kind of dimensions?
Well, it will depend on the dimensions through the integrals that give you the expected values. So this is an expected value inside the time integral. This expected value is an integration over all the dimensions that you have. If the dimensions are very many, it is an integral over very many dimensions. How to deal with that, it's a whole technology of its own. Okay? But for instance, this kind of thing can be used in artificial intelligence, okay, or in machine learning, where you may have a huge amount of parameters, and that is that you can apply this. Okay? You can apply this, of course. There are techniques that are developed specifically within statistical mechanics that is done precisely to deal with many dimensions, okay, as I told you at the beginning. In a dynamical system of 1 or 2 dimensions like the ones I have implemented in MATLAB codes, you can get results much more easily than this. Because if you have a few dimensions, all things are easier. Yeah. No, yeah, I wanted to say that even 6 or 7 dimensions, however, could be very large.
Yeah, so do we have any system we can calculate the complexity when the dimension increases?
Yes, yes. There are various things that you can do, and various things that you find out. For instance, okay, if you have a one-dimensional system that is a solution of a simple differential equation, you just solve that. If you have x dot equals minus x, now you compute whatever you like. Okay, say this is defined in R. Okay, and so you could have a Gaussian F0. Something like this, where you can do calculations directly. If you go to 3, 4 dimensions, 5 dimensions, things start to become complicated. To do the direct calculation of this. Okay? So you have to start to use some indirect way of doing things. This is an indirect way of things. But it becomes efficient when the dimensions are very many. So there is, strange enough, okay, I have papers on this, if you're interested. Strange enough, in high dimensions, if the dynamics are sufficiently complex, the statistics is easy. If you go to lower dimensions and the dynamics is still complex, chaotic, then things are reasonable. If you go to situations in which the dimensions are not just one, and the dynamics are not chaotic, in the sense that they have no exponential divergence of trajectories, then that situation is the hardest to control. So, curious enough, it is more difficult to deal with a non-chaotic dynamics in low dimensions than with a chaotic dynamics in high dimensions. Because chaos and many degrees of freedom favor the statistical properties. Statistics becomes what happens, okay? But, you know, it's like coin tossing. If you toss a lot of times, you will see that more or less you get half and half. It's not easy, eh? Your thumb gets tired before you get half and half. But you can reasonably approach it. Building statistics with large numbers is often successful. Same thing with dimensions. When there are not many, and when the dynamics are not sufficiently complex, then there is another kind of complexity that makes things unpredictable. I'll just give you one quick example and then we go. Then you have to formulate the question case by case. Okay? But suppose you have a single particle that bounces off walls that are straight lines, polygonal walls. Okay? These are models, for instance, of transport of various kind of things in nanoporous membranes and so on. Okay? Now, if the walls are straight, the trajectories are simple to compute. You go from collision to collision with the wall, you just reflect, and you go on a straight line. This thing is the hardest mathematical problem that I have seen so far. If you want to know at which rate these particles move through the channel. Because it is enough that you change the slope of the walls by nothing, and the result changes completely. So the dynamics are trivial. Dimensions is sufficiently low, okay? But to know what happens in time is almost impossible, okay? While if you make these walls round, even only one, okay? Then when you collide, you have a so-called defocusing effect which separates trajectories much more. Okay, this is easy. Making the dynamics chaotic makes easy the statistic. Okay, so you see, there is a variety of situations. I don't have a single answer to your question. At least I gave you an idea. And people in big data and machine learning, I believe to some degree, unconsciously or not being aware, they have hoped that they have sufficiently complex phenomenon with sufficiently many degrees of freedom. The more complex and the more degrees of freedom you have, the easier it is to make a statistical prediction. In one dimension, you don't have chaos. In three dimensions, you can have chaos. Okay, that again is bad again, because there it only makes sense to follow the single trajectories, and they're chaotic, and then you don't know where they go. So, okay? Okay. Sorry, made it a little long. What time do we reconvene for the tutorial? 2:10. Ah, today we have plenty of time for lunch. Yes. Yesterday we had 15 minutes, then Sivaraj's generosity allowed us to stay. almost 1 hour. Okay, I see you later with those of you who are coming.